Hello everyone, in this video we are going to see how to square and cube a number which is stored in 8051 microcontroller. Now here you can see that there are two sequence of blocks. In the first sequence we can see the address locations 8000, 8001, 8002 and so on. This block is going to be storing the program. Meaning whatever we are giving instructions to the 8051 microcontroller, that instructions are going to be stored in this block. So this block can be called as the program memory. And the another block which you can see on the right is the data memory. Because in this block we are going to be performing the actual thing which we want, the square of a number and the cube of a number. Now in 8051 there is a register called as the DPTR register, which is a 16-bit register. Also keep in mind that both these blocks are from external memory. Now first I'm going to point the DPTR to a specific location in the external memory 8100H. For that I'm going to write the assembly language program as MOV DPTR, whatever address location I'm using. So MOV DPTR, hashtag 8100H sets the DPTR to that 8100H location. The next thing which I want to do is in this 8100H location there will be a data value which will be present inside this address location. Now what I want to do is I want to copy this data value into another register called as the accumulator, which is present in 8051. So I am going to store whatever is present in 8100 in the accumulator. For that I am going to write MOVX. Why do we use MOVX? Because we are accessing external data memory and we are moving it inside the 8051 microcontroller. The accumulator register is present inside the 8051. That is not part of external memory. So since we are accessing the external memory and bringing it inside the 8051, we have to use MOVX. And I'm going to write A, at DPTR. So I have loaded whatever is there in this location, whatever the DPTR is pointing at, the location, into the accumulator register. Now there is another register in 8051 called the B register. I am going to store the same value which is present in A into this B register. For that I have to write MOV B, A, meaning I am storing whatever is present in A into B, or I am copying the value from A to B. Now I am going to use another register R0 to store the same value of A. You will understand why we are doing this later. And the assembly language program for that is MOV R0, A. So I have successfully copied whatever is in A into R0. Now I'm going to perform the multiplication of accumulator and the register B. So I am writing MUL AB. Now if we multiply these registers, it is going to result in a 16-bit register. This 16-bit register is going to have a high byte and a low byte. Each byte is an 8-bit result. Now when we multiply A and B, the B is going to be the high byte and the A is going to be stored as the low byte. The high byte is also known as the most significant byte. And the low byte is called the least significant byte. In total, this is a 16-bit result, and the high byte is stored as the MSB and the low byte is stored as the LSB. Now I am going to increment the data pointer register to the next location. In this instruction, I have incremented the data pointer register. Now the data pointer is pointing to the 8101 location. Now after this, I am going to assume that we are going to use only the low byte. We don't need the high byte because I am going to be only dealing with small numbers which are within 8 bits. So we don't have to consider the high byte, which is the next 8 bits. Since we can't deal with huge numbers here, we are only dealing with 8-bit numbers and therefore we are only going to take A. Remember this though, both A and B have the same values, which is a small number, and when we multiply those two small numbers, the square of them will be stored in A. They are small, so they will fit inside 8 bits. We don't need to assume this high bit because it will mostly be 0, 0, 0, 0, 0, 0, 0, 0. And only we are going to consider this 8 bits. Now, since I am interested only in the low byte, I am going to copy this into this location, which is pointed by the DPTR register. So for that, I am going to write MOVX. Again, since we are copying the value within 8051 into the external memory, we have to use MOVX, not MOV. So MOVX at DPTR, comma A. I have stored whatever is in A here in 8101 location, which is the data pointer location. Now I'm going to be copying the value at A into B. So now B has the same number or value as A register. Since we are dealing with only inside the 8051, I'm going to use MOV B comma A, meaning I have transferred whatever is at A into B, or copied whatever is at A into B. Next, what I'm going to do is I'm going to use this R0 register, and I'm going to copy whatever is stored at R0 into A. This is the reason why we have defined another R0. So I'm going to write MOV A comma R0. I have copied whatever is at R0 into A. Now I'm going to perform the multiplication of A and B. MUL AB. Remember that B is a register which is containing the squared result and A is the original number. So since we are multiplying the same value, the squared into that value gives a cube result. The squared value was calculated here itself. In the first mul AB, we have calculated the square and we have stored it in A. But here, since we are multiplying the squared result with a single value, we are going to get a cube here. The cube value is going to be got in the second mul AB. Now we have stored the squared result in 8101H location. Now we want to store the cube result in another location, probably 8102. For that, I am going to increment DPTR. Now, just like how we stored the squared result by MOVX at DPTR comma A in 8101 location, I am going to define another MOVX, another MOVX at DPTR comma A. So the cube result is going to be stored here. Also, the DPTR is pointing to this location 8102H. Now I have to halt the program. For that I am going to write halt sjump halt. So this instruction causes the program to jump to itself and therefore effectively halting the program. Now we are going to be implementing this ALP into the practical 8051 microcontroller. For that we need to know something called as the opcodes. Usually opcode sheet will be given. So in that opcode sheet you will have numbers assigned to every instruction which you are using. So you have to see the opcode sheet and give the corresponding numbers to whatever program you are using. Now for example, for MOV DPTR we have an opcode 90 and the address we have 8100. We have to separate it into 81 and 00. So this 90 is going to be stored in 8000 here, and the 81 is going to be stored in 8001, and 00 is going to be stored in 8002. Now the 81 and 00 came because we are storing the data value at that location. If you are using some other location 8500, then you have to use 85 and 00 as the opcodes. And in the next instruction MOVX A comma at DPTR, if you see the opcode sheet, you will have the opcode as E0. So E0 is going to be stored in 8003. So these are the complete opcodes for their respective instructions which I have used. You can refer the opcode sheet for the correct opcodes. Since it's because impossible to memorize all the opcodes, you can refer the opcode sheet for the opcodes. The only thing which you should know is how to write the program, and you will be able to remember the opcode easily. Now we will implement this in the practical 8051 microcontroller. Now, we are going to give an example of how the square and the cube of that number is performed. Now let's take an example value. Let's take 6h. This 6h is going to be stored in 8100h. Now if we square this, first let's convert it into decimal. The decimal equivalent of 6h is 6. Now if we square 6 decimal, then we are going to get 36 decimal. Now we are converting this 36 into hexadecimal. If you use a converter, or you can convert it using manual method also, you will get the hexadecimal equivalent as 24. Similarly, if you cube the decimal value of 6, you're going to get 216. 36 into 6 is 216 in decimal, and if we convert this into hexadecimal, you're going to get D8. So this is what we are going to get in the practical microcontroller. So let's see how we get that. Now this D8 is the hexadecimal equivalent of the cube of the 6, and 24 is the hexadecimal equivalent of the square of the 6.